All right, so to kick things off, I'd just like us to go down the panel here and have everyone briefly introduce themselves and maybe give a couple minutes of remarks. So I'm Zach Manchester. I'm a new faculty member here in AeroAstro, and I work on primarily small spacecraft. And I'm interested in this topic for a long time. I think this is great to be here.
I'm Sigrid Close. I'm an associate professor here in the AeroAstro department. Been here for about 8.5 years, and I work primarily on hypervelocity impact plasmas.
I'm Ellen Ancona. I work in Germany at EUMETSAT, where we control meteorological satellites. But I'm here for my master thesis research, and I did some study on solar sail mechanism, including thermal desorption. And so that's it.
Okay, I'm Harry Atwater. I'm a faculty member at Caltech. I'm interested in nanophotonics, which is the field of how light interacts with nanoscale structures. And that includes a wide range of potential applications, including energy and information systems. And in the context of Starshot, it very much impinges literally and figuratively on the light sail.
Hello, my name is Saidi Fern. I'm a professor of physics at Cal State University Fullerton, and I'm basically interested in making a star drive. I want to go interstellar. I want to get out there. My area of research is with Professor Woodward, and we've been working on the Mach effect drive, or mega drive. It's Mach effect gravitational assist drive. So if I'm allowed to describe that just a little bit, I will go ahead. So actually, Sonny White gave you a nice demonstration of a liquid drop. It was a drop of silicon oil bouncing on top of actual silicon, a very thin layer of silicon inside a Petri dish. And the Petri dish was sitting on top of a loudspeaker. So I don't know if you mentioned that the loudspeaker was being powered, of course, and the loudspeaker was being oscillated at maybe 80 hertz. Right? So at 80 hertz, it's just below a natural frequency where the silicon would start to make waves, Faraday waves. Right? So it's just below that frequency, so that the silicon is actually nice and flat, like a flat lake. And then what happened was they took a toothpick and pulled a little piece of oil out of the liquid and let it settle as a little droplet. So that normally the droplet would absorb back into the silicon, but there's a little bit of air film in between, so it actually can start to bounce. And that bouncing, the ripples, the ripples are formed because the oil's actually being excited. So it's just below what's called a Faraday frequency, and then the bouncing can generate these waves. Now, as you saw, the waves the drop can land on the side of a wave and actually be propelled forward. So the kinetic energy of that propulsion is actually coming from the energy that you're putting into the silicon oil via the loudspeaker. So what I'm suggesting is, imagine, I'm going back now to gravitation, because this is a gravity assist drive. So imagine a rubber sheet, but it's not just an ordinary rubber sheet. You have to pull on the end, so it's been tightened. So you're really torquing the ends of or pulling on the rubber sheet to make it tense, so it's got tension in it. And then you put a mass on it, and of course you get the indentation. But imagine the mass can fluctuate in weight. So it can get heavier, and it can get lighter. It can get heavier and lighter. So you'll have a bouncing, right? And that bouncing is going to make ripples. So what I'm suggesting is that the Mach effect drive does have this element that can fluctuate in mass by a very small amount, a delta m of about 10 to the minus 8. And that small mass fluctuation can be used by exciting the gravitational excitation. And you're basically pulling energy out of the gravitational field, which is under this tension. So it's the universal gravitational field. So you're tapping into that. And that's what's giving you the kinetic energy of motion. So anyway, I just wanted to mention the drive itself is just there's a brass mass, there's a piezoelectric stack, and then the end plate, and of course the stack is between several bolts. And so you're making the piezoelectric stack oscillate. So it's got internal energy changes, and it's accelerating. And because it's got internal energy changes and accelerating, that's what's giving it the ability to fluctuate in mass by a small amount. And that mass fluctuation, if you imagine it pushing on something when it's heavy and pulling back when it's light, pushing when it's heavy, pulling back when it's light, that gives you the direction of motion. So you can think of it as along the asymmetry of the two masses. But the actual energy of the motion is coming from the gravitational field and basically distant matter of the universe. So I think I'll stop there. I'll talk more about it if you want to ask questions.
Hi, I'm Mateusz Józefowicz. I represent I think as the only one, he represented an SME, which is a great honor, and maybe this is a sign of times, and I would like to take this opportunity to thank Pete Warden and the Breakthrough Foundation for inviting us, because we are not representing a big institutions, but still we are working on concepts that will allow us to discuss in this great panel. We are based in Toruń, Poland, and we are building a capability of having an independent operational capabilities, so which in case of new space companies might be possible to some extent. So we've been examining propulsion concepts, and one of what appears to be a conventional concept, it's a solar sail material that we have been awarded at Luxembourg Space Exploration Sustainable Exploration Prize, and I will talk about it. But we've also developed tools that allow for validation of what you can call exotic drives. So we are very interested as a company in exotic drives, but not all of our team are scientists. But we want to build stuff that works. So first of all, we develop tools that can validate concepts that can be discussed here. And I will tell you about it more as well.
Okay. Good afternoon, I'm Kelvin Long. So I was originally an aerospace engineer, then a physicist, did a doctoral work in laser fusion. And I saw a job advert in New Scientist in England saying, do you like rocket science? So I went for the job, and it turns out it wasn't rocket science, it was thermonuclear weapons design. So I did that for 12 years. I never used to be able to say that, but I left that world 2.5 years ago. So I have a particular interest in Orion, which is one of the historical concepts that Freeman Dyson used to work on, of course. And I'm also interested in fusion propulsion. My entrance into the interstellar community actually was through warp drive. So I did a master's in astrophysics, and I was really interested in general relativity and cosmology. But I was intimidated by the vast number of papers, and I thought, how can I possibly contribute to this field? So I discovered Miguel Alcubierre's paper on warp drive, and I thought, okay, maybe I can contribute to that. So I spent 2 years on warp drive, and concluded it was, I don't use the word impossible, but I say prohibitively difficult. I identified something like 19 physics and engineering reasons why it currently doesn't work. So I moved on to something more practical, fusion propulsion, and particularly with Project Icarus, which you might have heard of, which is the successor to the original BIS Daedalus project. And my speciality in particular is inertial confinement fusion, so that's one of the subjects I used to study. And I then moved on to laser propulsion. So Jim Benford, if he's here, would argue I'm getting more practical as time goes on. And I work with Starshot on the Breakthrough Starshot project, which is why I'm here. I'll just say two brief things about interstellar propulsion. The first is that there's a lot of interesting speakers today. Some you might put in the exotic propulsion camp. And it's good to see some of the, as usual, rigorous scientific debates. It's quite intimidating having Lawrence Krauss sitting in front of you. So I feel sorry for Sonny White talking about his particular propulsion concept. But I'd remind you that it's only by pursuing such wild concepts that we make breakthroughs. I mean, Frank Whittle in the UK, when he first proposed a jet engine, he was essentially laughed at. The Royal Air Force concluded there was no practical application for this device. It's only when he came to America that things started to happen. So I think it's important to foster an atmosphere of, yes, rigorous science and always holding people's feet to the fire with experiment, but also encouraging people. So I would just say that. The second thing I would say is that there's a lot of focus on the distance between the stars. And this also feeds into the SETI debate from the absolutely outstanding talks we've had the last couple of days from the astrobiology community, which I was very impressed with. But there's not a lot of thought about time. Of course, Einstein taught us that time is a major issue. We think of space-time rather than space and time. And actually, we know that if you travel off into the universe at some 999 fractions of the speed of light, you get relativistic effects. And what nobody talks about is the time dilation factor. So everybody in this room, effectively relative to the reference frame of the Earth, is moving at a total speed equal to the speed of light. And as soon as you start accelerating through space, all of your motion goes into the time dimension, which is essentially what time dilation is. That's a sort of toy model to understand it. And so if you imagine, if we can get to the center of the galaxy, for example, in 28 years, which is what Carl Sagan showed in his 1960s paper when he applied Einstein's relativity, But back home, of course, is long gone. All of the people that you knew and all of the loved ones you knew are all gone. So this is the impact of relativistic time dilation. And similarly, if you imagine that problem applied to the entire galaxy and thinking about search for extraterrestrial intelligence, and they're all moving off at different speeds relative to their source of origin, different relativistic time dilation factors, this becomes what I call temporal spaghettification. It becomes a very complex scenario. And I think that has implications for understanding the Fermi paradox and why we apparently don't observe intelligent life in the universe. So we've got lots of things to talk about, propulsion in particular, but I'll let Jeff introduce himself.
Well, I do interstellar talks often enough to have one canned, but thanks to Pete for putting me on the panel at the last second. I'm Jeff Grayson, repeat offender in commercial space. I've been an entrepreneur since the late 90s there. And most currently wearing 3 hats that all came to a magic convergence here. I'm the CEO of a rapid prototyping aerospace vehicle company. I'm the CTO of a beam power propulsion company, and I'm the chairman of the board of the Tau Zero Foundation, which is a nonprofit for interstellar propulsion technology. So I, in theory, have something to say. There's so much creative thinking about interstellar, and it's very hard for somebody looking at the field who doesn't live and breathe and swim in it to kind of get their arms around it. You can clear away a lot of the clutter by just realizing that unless something really surprising happens in the world of breakthrough propulsion physics, and I don't just mean little surprising, I mean, like dragons and magic and teleporting shocking. The conservation of momentum and the conservation of energy will still be with us. So if you want to cover a lot of distance and you don't want to take a lot of time to do it, the velocities have to get high. If the velocities have to get high, the energy has to be large. There's probably no getting around that. And even if you posit either known physics, pushing against the interstellar medium, pushing against, reacting on photons that are available, or even if you posit unknown physics, you're probably still subject to, what I, as a propulsion guy, call the propeller equation. The amount of power it takes to produce thrust goes up by pushing on a medium, goes up the faster you're going with respect to the medium. And there just ain't no getting around that unless something really shocking happens. So any way you slice it, we're going to need a lot of energy. The reason why people keep talking about beam propulsion is very fundamental, which is if you want to carry a lot of energy, you want to get a lot of energy, it's really helpful not to carry the generator with you. And one of the things that we're doing at Tau Zero is kind of looking over the whole field and trying to find ways to do equal yardstick comparisons of the merits of the different ways of looking at it. It's already clear what is from a fresh look, what is well known to others in the field, which is the longer you can stay in the beam, the better, because that lets you, you buy beams by the watt, you acquire joules by the second. So if you have a certain size beam and you can stay in it 10 times as long, you can get 10 times the energy out of it for the same power beam. And that's the reason why I mentioned in the question earlier that I'm getting very interested in the class of sail beam concepts that, sadly, the originator of which is not with us anymore. But there's a lot of interest there because that gives us a known physics way to think about carrying energy over longer and longer distances to credibly small spacecraft. And I'm actually quite optimistic that not just about that concept, but about the whole class of concepts. It's great to be seeing it taken seriously. It's great to be seeing people actually funding studies within government, within the private sector. There's a huge, long way to go. It's early days yet, but I think to look at this problem and say, oh, it's just too hard, is not a realistic assessment of where we are. There's lines of attack within physics as we know it. There's interesting hints of physics as we don't know it, but my guess is either way you slice it, we're going to have to pay for the energy, and I think that we have ways to do that.
All right, well, thanks, everyone. I think to start things off, I'm actually curious, as a follow-on to what you just said, Jeff, looking at different lines of attack and the many options out there and approaches. If you, say, had $1 billion today, where would you put it if you had to make a big bet on these technologies?
I'd put it in beams, broadly speaking. There's more than one way to skin that cat, and it's in my opinion, very premature to pick a winner. because photons come in more than one frequency. The different generators of photons have very different dollars per watt figures of merit, and there's fundamental physics reasons why that's not likely to change tomorrow. Lower frequencies are going to be cheaper per watt than higher frequencies. Lower frequency beam directors are going to be more expensive than high frequency because they're going to be bigger. Particle beams, I think, are understudied right now. There's a lot of hand-waving about, well, particle beams have high divergence. It's not at all clear that that's a law of physics problem. It looks much more to me like in the 1980s, when a lot of work was done on particle beams, we were trying to shoot things down from orbit, and the Earth's surface is only so far away, so you only need so tight of a beam. Alpha Centauri is farther, so we need a tighter beam, so it's worth working on the problem. The beauty of particle beams, for those, again, who don't swim in this field, is when you shoot reaction mass, like photons, at something, and the reaction mass is going enormously faster than the ship, most of the energy is wasted. That's why rockets work better at high speed than they do at low speed in energetically efficient terms, because you're using the reaction mass energy more efficiently. Photons are as fast as you can go, so they're as wasteful in energetic terms as anything you can possibly do. If you can do a particle beam and if you can hold it together over the requisite distance, you can turn up the speed of the particles as the ship starts going faster, and the energy savings is quite significant. And there are magnetic sail options where you can think about making a much larger target than the physical sail that you could with a photon propulsion system. So again, if I had $1 billion, I wouldn't just pick a winner. I would start a technology portfolio, because I think these approaches all inform each other, and the chances of getting a successful outcome are higher if we do some of the fundamental technology work.
All right, thanks. Now I'd like to pick on Harry, actually, as someone who's got a deep knowledge in many of these sort of sail material problems. Where do you see the long pole in the tent technologically? What do you think the hardest problem to solve will be?
Okay, well, first of all, I wanted to reflect back to Jeff's talk, which was an excellent overview of all kinds of concepts for beamed and pushed sails. And he was the one that really had the bold insight that a dielectric sheet is the key aspect that we need for very high power density beamed sail propulsion. So what's interesting about this is the date when he made this observation and his paper was published, because since that time, we've had essentially several revolutions that have really brought us today to a lot of opportunities. One, there has been a revolution in the last 15 years in photonic design of materials. So I think at the time that Jeff was thinking about his sail, you think of light more or less in a ray tracing sense, specularly reflecting from a planar surface. Since then, we've developed all kinds of engineered materials where the angular distribution of the scattered and transmitted light can be controlled at will in sheets that have basically sub-micron thickness that have very, very low absorption. So I think that's a really important insight. That partly is because we've developed techniques for doing another revolution, which is this huge growth in computer power. We can do very sophisticated models, full wave electromagnetic simulations over large scales. We can fabricate structures in almost anybody's lab nowadays that have you can make many of the structures that you would like to make. Another thing, somebody mentioned the Nobel Prize for graphene. That's another one of the revolutions that's occurred. There's been a real revolution in layered materials. The ability to make materials at the wafer scale that are anywhere from a single atomic layer to 100 nanometers thick. So graphene is just the first of a whole class, for those who are not in the field, of two-dimensional and layered materials, dielectric, metallic. It's completely exploded into a whole field of physics that condensed matter physicists are studying. But technologists are also embracing these materials because they have extreme properties. Many of them have very extreme properties like graphene. And we can begin to use some of these things together to address some of the key aspects for the Starshot light sail, namely extremely low absorbance, extremely small mass per unit area, that basically drives a thickness for most ordinary materials, less than 100 nanometers thick for the whole thing. And also a combination of high reflectance and high thermal emittance in the infrared. So almost all space problems that I've encountered ultimately turn into thermal problems. And the thermal problem is the biggest challenge for the light sail. We also were given some gifts from LIGO, which looked at, for example, ultra-low absorption coefficient structures for mirrors. And so we know of materials now that have absorbances of somewhere between 10 to the minus 4 and 10 to the minus 8. And that's a really crucial sort of tool to have in our toolbox. And then being able to combine that with something that can radiate thermal energy efficiently to the cold background of space to make the temperature stay in the few hundred Kelvin to say less than 1,000 Kelvin range at these megawatt per square centimeter power densities. So I think that's so what's the tall pole in the tent? I would say at this point, the tall pole is something where you're, a domain expert, or at least a contributor and early pioneer, and that is controlling the stability. I think but all this ability to control the angular dispersion, the optical dispersion, gives us new tools also. So I think even since last year's conference, I'm much more optimistic that we may have some ability to create passively stable designs for the sail.
Great, thanks. So maybe in the interest of spreading things around a little bit and expanding our portfolio, maybe we'll try Kelvin. What would be your second bet, if not the light sail concept? What's another one that you like?
That's a difficult question. Well, I happen to be a fusion fan, but I do appreciate that fusion is always this kind of 40, 50 years away, right? Although having worked, in particular communities, I know what is possible. But trying to do it in a laboratory environment like the National Ignition Facility is very, very difficult, and it's also very expensive. There are ideas, for example, from Robert Bussard, who also invented the interstellar ramjet concept for looking at electrostatic fusion concepts. And there's lots of ideas like that which could be pursued. But actually, I'm sort of changing your question a little bit, going back to the billion-dollar question. I wouldn't actually go for a second option because I think that laser cells is the right approach. But actually, if I had $1 billion, I would plug it into experiments, foundational experiments. There's basic space demonstrations you can do, like with CubeSats, going around the moon to demonstrate cells and laser cells and particle beamers and things like that. You can do those cheaply for millions or tens of millions of dollars. But if you had $1 million, the amount of experiments you can get done to verify or open up new lines of inquiry in physics on things that we don't understand, and there's so much that we don't understand. That's where I prefer to put the money as an investment program over the next 10, 15 years. And then you start to get to a position where you can make the proper decisions. One of the issues with this community in particular, the interstellar community, is there's a lot of advocates for specific propulsion methodologies. And this almost becomes like it's their life's work, and they're going to kind of fight for it. But actually, if you look at most of the studies that have done, they're very apples and oranges comparisons. There's very few systems integrated full systems designs of starships or even spacecraft which use advanced propulsion systems where they're compared on a like-for-like basis. And I'd like to see more of that because that's only when you can really tell where the sort of optimum trade-offs are. And one of the things I'm particularly interested in is hybridization, the idea of taking multiple propulsion systems, combining them together. So the idea is you're trying to trade mass in particular for performance. And I think that that's something that's not been done. It's been done on paper. A few examples, for example, one of the problems with Project Orion is that its specific impulse is limited by the length of the shock absorbers and how fast you can quickly absorb that energy, but also the attenuation of the particle flux. So when you get these units detonating, we call them units in the civil world. So one of the ways to get around that is something called the John Dow Solem Medusa cell, which is this big spinnaker concept where you have extended lines and you can actually increase the specific impulse performance quite considerably. And so I think we need to think along those lines where we combine sort of electric ion engines with reaction engines and cells and laser cells, where you're actually trying to reduce the mass of systems but to get maximum performance. Just to finalize, if you go back to the original StarWisp concept, you're talking about something that's a Fresnel lens about 1,000 kilometers across. pushing something like tons or less payload to 11% the speed of light using a frontal lens that's about 560,000 tons in mass. You compare that to Daedalus, which is the 1978 fusion study. That was 50,000 tons of deuterium helium-free fuel, 450 tons AI probe. So however you do it, and Bob Forward said this himself, interstellar travel is hard. It's expensive, it costs energy, it costs a lot of power, but it doesn't seem to be impossible. So however you do it, it's going to cost a lot of energy, a lot of money. And so to me, to reduce all of that, you need to go into optimization and hybridization concepts. And that's something that's not really been pursued with vigor.
Can I riff on that for a second?
Please.
Totally agree with that. One of the things that surprises me, I've been reading about this for 30 years, but I've only been working on it really actively for the last 2, is how little cross-fertilization there is between the various concepts in the field. It's been a while now since the magnetic sail was invented. Thank you, Bob. And yet people are still talking about, we can only do flybys because it's too expensive to stop. It's not true. We know how to stop. You just don't stop using the same thing that you start with. That it doesn't matter that it came out of another lab. You put the pieces together. There's a lot of partisanship between reaction engines and sails. Look at the rocket equation. The thing you do with a reaction engine is you make second stages with it, because the faster the kinetic energy that you have when you start turning on the rocket, the more you get out of it. So it's much better to put a rocket to get from point 2 to point 3 C than it is to get a rocket to get from 0 to point 1 C. There's a lot of room to get by moving past the question of whose idea is better to the question of how do we design a mission.
So maybe broadening things just a hair, mostly because I'm curious. Sigrid, I know you work a lot on particle impacts and things like this. Mm-hmm. So what are your thoughts on the survivability of a mission like this at high speeds?
Yeah, I question it, specifically with the last talk in terms of the micrometeoroid impact, because it's not just mechanical damage that we're looking at now, but we're looking at plasma generation as well. And so how would that impact any type of sensors that you might have on the surface? But then just more broadly speaking, I think kind of as new to this community, wondering why there isn't more crossover with, you mentioned hybridization, traditional ion thrusters. I didn't hear any mention of the VASMIR, although I know that's a little bit controversial. Yeah. So maybe I'll throw it back to the panel about how much do you look at the fundamental plasma physics and what's already been done quite a bit over the past 30 years to integrate into interstellar travel. So,
you're obviously guided by the TRLs. That's the first thing. I'm trying not to mention VASMIR because is Bob still in the room? I don't want to cause a big argument. So I went to.
I'll cause the big argument.
I went to VASMIR last year. Had a tour of the labs. I was quite impressed with their efforts. And I sort of go back to my original comment, but I think it's good to encourage things. Anyone who's exploring a new area. But certainly, I mean, from my perspective, because I don't really do experiments, sadly, I wish I did. In my previous job, I was involved with experiments. They were mostly analyzing experiments, which are very big bang experiments, if you know what I mean. And that was very interesting. But these days, my work tends to be theoretical. So at the very least, there's things you can do on paper. Theoretically, you can do what I would call apples and apples comparisons with different systems. To me, actually, we're talking about propulsion, but actually the most important thing is what payload mass do you want to deliver to your target, and therefore what science do you want to get done, or whatever it is you're trying to achieve. And so, Starshot, which is an absolutely inspirational program, which I'm happy to be a part of, is wonderful, but it's a gram, and that's kind of sobering. It's a gram. Now, how much can you get done with a gram that's going to be launched in maybe 20 years from now? Hopefully a lot, but it'd be nice if we could send more. And so, but at the very least, on paper, you can start to look at those things and get an idea of what sort of power levels are required. So I'm not sure I've answered your question, but I think hybridization is the way forward as a trade-off with mass and performance. Yeah.
I agree.
I'd like to chime in on that one. The challenge with any particular electric thruster is there's a lot of focus on the thruster. Mm-hmm. The thruster is not the problem. Right. Power supply is the problem. Right. It's the same thing in chemical rockets. People always want to see the pictures of the big flamey bit, but that's in some sense the easiest part. So if you from time to time, people come out with very strong claims for what we could do with a certain kind of electric thruster if only we had a magical power supply. And that would be wonderful. And if we had that power supply, there's probably 28 other thrusters that we could also do wonderful things with. The problem is the power supply. If the kilowatts per kilogram is very low, even if the energy content of the power supply lasts through the entire mission, it takes so long to build up a high velocity that the trip time ceases to be all that impressive. So that's the reason why I think we've had better thrusters than power supplies for 30 years now. And the thrusters keep getting better, but the power supplies kind of don't.
Just to say quickly, the Starshot is like 100, 200 gigawatt beam, but the Daedalus concept from the 1970s, this sort of 50,000 tons plus system, this required a specific power of 40 megawatts per kilogram and a jet power of about 10 terawatts. So however you do it, it's a lot of power, right? Which is exactly what you're saying. So.
I think the application, I think if there was more discussion maybe between the two different communities, I totally agree, it's all about the power supply.
Yeah.
But there's not people aren't looking at that as being as necessary as within this community. So maybe if there was more discussion between the two, I think that maybe that area would have more progress than it has been.
Yeah.
Well, if this antimatter breeder works that was being talked about earlier,
Yeah.
you know, that'll be major cool.
So maybe we're ready for some audience questions. All right. I guess I have the microphone tossed, so heads up, everybody.
First try.
Good throws.
Getting to the stars was that easy. This is a question for Harry. By the way, thanks for our little discussion on Monday about the possibility of holographic sails. I also got another group interested in this. This was a group at New York City College of Technology. One of the people was Eleanor's master's thesis advisor. And basically it is, can you make graphene more reflective? And they say that there are theoretical approaches to making monolayers highly reflective. As most people know, they're essentially transparent. You can make them absorptive by adding something I'm not going to be able to pronounce at this time, molybdenum, I believe. Did I do that right? I think it was pretty close. Okay, so do you know of any way to make a monolayer more reflective, or highly reflective, let's say?
Yes, but you'll be disappointed at the wavelength at which you can do it, which is in the tens of microns, maybe 30 to 50 micron range.
And there was no atmospheric window there.
Yeah. So the issue is that if you go back to just the fundamental electronic structure of graphene, graphene is what we call a semi-metal, sort of a hybrid of a semiconductor and a metal. That means it's never has purely dielectric properties like a semiconductor. It's always absorbing. And when you go to these megawatt per square centimeter power densities, so graphene, as we talked about with the solar sails, is a perfectly good material when the power densities are low, when we have sunlight. But at the megawatt per square centimeter, so the megawatt per square centimeter, by the way, to an optical physicist, this is not a very forbidding power density. This is still orders of magnitude below the onset of nonlinear optical processes in typical dielectric or semiconductor materials. But it is pretty high to think of, and essentially rules out, I think Jeff said it well, it rules out most things that are metallic. Metallic materials are very interesting. They absorb by free carrier absorption in the electrons in the metal. The reason metals aren't black is because they have such a high real part of their permittivity or their refractive index that the skin depth is very small. So they absorb a little bit, even though the density of electrons is really high. In an insulator, you do the opposite thing. You make the electron density be close to zero, and you allow the electromagnetic waves to penetrate all the way in. So graphene is in this sort of intermediate regime so I think it'll be good at low power densities, and at long wavelengths, where it starts to look more like a perfect metal, but it's going to be tough for Starshot.
Okay, thank you.
All right.
You to throw the other one out into the other side?
Think I can make it?
I think so.
Just a brief comment that in principle, there is a shortcut to figure out which method is the best. And that's by viewing the sky and looking for other civilizations that worked on it for 1 billion years and by now have devised the best method. And so that brings me to the point that the fundamental question is whether we can detect any such a spacecraft that originates from another civilization, depending on the method they use for propulsion. And I would be happy to hear your comments on that. Of course, it depends on the size of the system, and the size is dictated by the energy source. So if you can project to future technologies, that we might be able to achieve in centuries from now, what do you think would be floating out there, roaming through interstellar space? And do we have the ability to detect it from a distance?
Well, I'll venture, I'll throw this back at you and say, I think you've been a proponent of the idea of looking for the signature of the light beam. And I think the light beam will be much more visible than the spacecraft itself.
And it has the challenge that the better we get at it, or better anybody gets at it, the tighter the beam is and the less energy spills past the ship. So you'd almost only want to be looking for somebody's first generation Starship, because by the time they do it a few times, they're going to be better at it.
Well, I guess one thing we can say is that if you see the light beam, you know that the sail is coming towards you.
Yes.
So I'm also, somebody said yesterday, I'm a fan of Carl Sagan. I forget who it was, but I'm also a fan of Carl Sagan. And one of the great papers that he wrote was looking at signals in the universe, that, like the WOW signal. And he found something like 33 other signals that were single events, so they don't necessarily pass the test of the scientific method, but they were interesting. And of course, recently we've had things like Tabby's star and the controversies of that, and the Umar interstellar asteroid, which came into the solar system. There's actually quite a good literature on this subject. I mean, Bob Zubin, who's I've not heard at the moment, but he's written some papers detecting, for example, the sort of reactions you get from a fusion engine or an antimatter reaction. Whether you're measuring synchrotron radiation or bremsstrahlung emissions, over what sort of distances you can measure those. There's even been papers on chromaticity effects of wormhole lensing. So if you had a wormhole, instead of having the usual gravitational lensing effect you get from general relativity with normal gravitating mass, with negative matter you get a chromaticity effect, which is a bit like a rainbow, which you can detect. They've actually done observations to try and see them, and they haven't seen any. I read a paper a few years ago looking at FTL in particular, and Anders will approve of this because he's a philosopher. I made a philosophical argument why I don't think FTL was possible. And basically it goes along the lines of if anybody if there's civilizations in the galaxy, given that assumption, and eventually, it takes millions of years, they will start to meet. Now, if any one of those civilizations develops FTL technology, then eventually everybody else will have it. And the reason that happens is either they give it to everyone else, or everyone now knows that it exists, so they try to copy it, and eventually they get there, or they steal it. Or it's a bit like how writing systems were discovered. So on Earth, writing was discovered independently among different civilizations. And so this is one of my reasons for thinking FTL probably doesn't exist, because we would start to see them flying through the solar system today, especially when you look at the timescales of the galaxy, the evolution of the stars, and how long it takes to travel between the stars. So, but I do think that suddenly Breakthrough Initiative should be looking for signals of extraterrestrial intelligence in the universe. But I would also say non-conventional definitions of life, such as the Fred Hoyle type systems with I don't want to go off on a tangent talking about astrobiology, but I think we are a bit obsessed with the sort of homeostasis definitions of life, and we need to think more about sort of Schrodinger's ideas of what is life, decaying to thermodynamic equilibrium, and thinking about systems that are dynamic and have entropy and energy change, and looking and seeing if they have structure. Penny was talking yesterday about looking for structure rather than just chemistry in the universe. I absolutely approve of that. I think that's right, because then you start to see organization, and that's the indications of intelligence. And I think we need to start doing more of that, and hopefully Breakthrough Avi will start to do that.
But I would add that this is like a perfect reason to study all potential propulsion means. Even if you consider them exotic or impossible, we should study it in order to understand potential ways that of contact with potential life. or civilization. But if you asked me what to choose, I would say that we shouldn't choose a strategy for several decades and focus only on one propulsion. We should examine the applications of each propulsion. And during this panel, I can perceive that we are kind of accepted that we have to launch from Earth anyway. So this is the biggest obstacle. So we are talking of interplanetary propulsion, interstellar propulsion, but we are not challenging the fact that the biggest obstacle is the launch. It's the cost of the launch, it's the availability of launch. So we should somehow challenge it. I'm not saying that we have a solution, but if we want to progress, if we want to make a revolution, we should challenge this as well. But speaking of different uses, I agree that hybridization is a very good way to combine propulsions. But what we besides of analyzing future exotic propulsions, we come out with also a solution that changes things because we proposed a solution for space mining industry. You can actually think of mining nanometal on the asteroids. So why should you put your nanometal in the container while you can put it on the sail? In this order, in this way, your sail becomes your container. So your cargo becomes the ways of propelling things. So if we think of actually giving a priority to any propulsion for the mining future space mining industry, which is with an economical driver, it's very important to not only research and curiosity drivers, but also the economical drivers are a must here. We can make our cargo propel itself. This changes the rocket problem actually, but this is only one application. So other propulsions should be also examined.
I was going to say that if I was looking for a very highly intelligent species and wanting to travel through interstellar space quickly, I guess to travel first class, you'd really want a wormhole. I just want to step through and not have to worry about the radiation and all the years it will take to get me from A to B.
There is no physical solution for wormhole that we know exists. I mean, all the because reversible, because they disappear, they pinch off on a time scale shorter than the time you can cross them, and you need also
negative energy density matter.
Well, you need an equation of state that is negative pressure, and we don't know how to make such a thing. So.
Well, there may be a possibility if more work goes into the gravitational theory of Dr. Woodward, that there is a possibility of actually being able to generate negative energy density matter, but that's in the future. Right now, we're dealing with propellantless propulsion.
Well, as of now, the DOE is investing in searching for, understanding the equation of state of dark energy in the universe, but not beyond that. We can't excavate that dark energy.
Unfortunately not.
Well, I'd like to add something to that because, breakthrough propulsion physics is an ongoing topic. It's part of the portfolio we have at Tau Zero. And I think it's a mistake to approach any of those concepts of breakthrough propulsion physics by saying, well, we don't know that there is such a thing, so that's the end of that discussion. What I find surprising is it's frequently, with a lot of these concepts, not too difficult to bound the question of, okay, imagine it does work. Is it interesting?
Well, that's science fiction.
Well, no, yes and no, right? Where the whole point of the discussion is we're trying to consider how we might guide our investments to learn how to improve our capabilities. It is appropriate that the majority of that investment go into things that work with physics as we know it, because that's where we know the payoff is. It is also appropriate that a non-zero portion of that goes to physics as we're not so sure about. But you can ask the question when you're confronted with a new idea before you jump to say, I've never heard of that before, it's not what I learned in school, so that probably doesn't work. You can also say, well, okay, take the paper at face value. Suppose it does work. Would it really be all that interesting? And what I find is there's a large fraction of breakthrough propulsion concepts that fail the second test. So you don't have to get into an argument about whether or not the proposed effect is or isn't real, the answer is, even if it is real, it doesn't change very much. You know, the people, it's often said that, you know, well, if we could change it was on one of the quotes earlier, you know, if we could push on the quantum vacuum, you know, that would be the end of all of our problems. It's not true. You know, the propeller equation is probably still going to apply unless we repeal the conservation of energy. You know, it's still going to take energy to push against, even if you imagine that you could push against the quantum vacuum, and I'm well familiar with the arguments why you might not want to think you could do that. But even if you imagine you could, when you run the numbers and say, if you could, would it really change everything? Not so much. You know, so that tells you that there's potentially other interesting places to look.
So Avi, just to turn that back on you a little bit, as you're a physicist. So I think science should be a process of discovery and exploration, right? So you've got to have programs, and you roughly know the direction you're going in. But sometimes it's good to have discovery and exploration, and you don't always know where you're going, which is kind of a lot of these propulsion subjects, which, if they're imaginary and they don't really exist, they're on the boundaries of science fiction or even in science fiction. And as you know, a lot of these ideas came from science fiction. They are a process of discovery. Now, let me ask you, why is it not okay for propulsion scientists such as Heidi, who's looking at alternative theories of gravitation to Einstein's general relativity, or Sonny White, who's looking at alternatives to Niels Bohr's interpretation of quantum mechanics? Why is it not okay for them to do that, but it's okay, for example, for people to look for alternative theories of quantum gravity, such as loop quantum gravity or string theory, when the experimental evidence for those fields is very tenuous at best?
Different theories of gravity. Actually, I think I can actually account for the Mach effect and the propulsion completely within Einstein's general relativity. I have dabbled a little bit in Hoyle-Nolliker theory just because it is completely Machian. It describes everything, one mass being due to all the other masses in the universe in a very, very nice way. And it just happens to have a scalar mass field. When you go into when you think of all the masses as being smooth and homogeneous, like a mass soup, if you like, then you get a mass field, and this mass field is basically like a scalar field, which can support waves, just like the ripples that I was talking about. In fact, I think even in general relativity, people have used standing waves as part models to describe black hole echoes. So it's not completely unheard of in general relativity using Einstein's theory as well. But you can certainly do it with Hoyle-Nolliker theory, no problem. That's still classical. I'm not talking about quantizing it.
I will be mean, but kind. History teaches us that history comes with an aid to us right now, because the ancients knew that the Earth is on the turtle. So they knew it. Then they progressed because they did the revolutions. So then they learned that the Earth is not on the turtle. It's on the turtle and on 4 elephants, yes, and so on. So that's the way we have to think. We have to, if there is some reason behind it, we should try to examine it, and this is how the revolutions appear.
I'm a microbiologist, so most of the discussion this afternoon was way over my head, but not all of it, and that's really the beauty of meetings like this, where I would never go to a regular meeting and hear about solar sails. What I want to say is that it is an opportunity to think about solving some general problems together when we get into rooms like this, and thinking about propulsion not as an end goal, but as a means to achieve something in the exploration of the space. We don't want to bring to other planets and other solar systems rocks. We want to bring instruments to measure things and to send back information, and that's another part of the equation. So when I hear about various means of propelling spacecraft, they all are grounded to the mass of the spacecraft. The other part of the equation, how do we build instruments, how do we build this payload that is miniaturized? And there's way less investment put into that part of the equation compared to the engineering of propulsion. If we can make instruments 10 times smaller, 100 times smaller, 1,000 times smaller, we open totally new possibilities to do the exploration.
I'd like to directly reflect on your observation there, which is, using this 15-year period since Jeff Landis made his, and there was a number of other seminal observations about push sales then. Think about what has happened in instrument technology. None of us had one of these things in our pockets 15 years ago. The things that we had were much less functional and they didn't fit in your pocket. But also, some of the work that is going on now on layered materials, monolayer thick materials, is making it possible to make instruments in single monolayers of materials. So I actually want to challenge everyone here to think about not only making point designs. Right now, our thinking about what Starshot is kind of oriented around a point design, a spacecraft traveling at 20% of the light speed, a gram payload and a gram for the sail and so forth. But to really expand, not only thinking about the propulsion technologies, but also expanding around that point design to think about if we could make instruments be a milligram or a microgram or something like that, what would the implications be for the scaling of the power systems and the energy that are needed? What functionality can we pack into an instrument that's even smaller? I can anticipate that by the time we've solved many of the propulsion problems, the instrument technology may have gone through an order of magnitude kind of revolution as well. So
I'd like to sound a less positive note on that one. I used to be in the electronics industry and kept up with it, and there are elements of the technology that are just improving, as you say, leaps and bounds. But it only takes one piece of the system not to be improving on that same scale, and there's always a heaviest piece. So I would love to just say we're going to solve the problem because every decade the entire spacecraft's going to be an order of magnitude lighter to get the same job done. But in order for that to happen, the instruments have to be an order of magnitude lighter, the power systems have to be an order of magnitude lighter, the onboard propulsion that you use to steer has to be an order of magnitude lighter, the communication system has to be an order of magnitude lighter. Ultimately that probably means the power per bit has to be an order of magnitude less, or the aperture, there's a lot of connected problems. So I actually think, there's a reason why aerospace systems going back 100 years always start by talking about propulsion. It is the driver. The other problems are all important. They do all have to be worked, but when you're looking at something where the propulsion is so many orders of magnitude above in terms of being the sizing challenge, and what your ideas would be about what kind of mission you would design change when you change your concepts about what the propulsion technology is going to be like. Like, are you going to stop or not? That's a pretty fundamental input parameter that goes into thinking about what your mission design would be. That's not to say that we shouldn't keep thinking about all those things. Well, the good news is a lot of those other technology curves are being pushed independent of whatever we might be doing in the world of space propulsion.
Yeah, that was my point, is that Starshot doesn't have to invest in it.
Right.
But
they're going to get better at the rate they get better, and we all hope it's good. But there's not a lot of other places to where people invest in propulsion technology outside of aerospace.
It is true, though, that if you look at what we're doing today, and so take the Mars Curiosity rover, the sample analysis at Mars, which is a quadrupole mass spectrometer gas chromatograph, is about the size of this catch box and weighs, I think, 40 kilograms, roughly, less than that, which, when I was a graduate student in the 1980s, would have filled an entire laboratory room if it was even possible to do those kind of measurements back then, some of which weren't. And so that, as Jeff says, that's happening, that things are getting smaller, and it does enable exploration of new worlds. One of the reasons is that NASA has programs that are very early stage, like the NASA Innovative program, but also in planetary science, and so I'm going to pass it to Jim Green, that invest in those early stage things. It would be nice if we could accelerate that to make things even smaller, and we've heard about some of those here with some work at Berkeley and microfluidics and other things.
There's a couple over there on the other end of the room. So since you've got it, if you want, go ahead, and then I'll toss it over there next.
I was just going to, as John said, I could expound a little bit on the investments what we do. But indeed, I think it's absolutely essential that we have these kind of low TRL investments. We have several programs for which we invest in low TRL, mid TRL, which is always the valley of death, and it always requires the big investments that go on. But we have to be able to step up to do that. It's the only way we're going to make progress, which buys down our risk in the long run when we actually launch our mission, because we've gotten our instruments ready. And they're not in the way of making the mission. Because in planetary science, it's all about the windows. If I miss a planetary window, it can be hundreds of millions of dollars before I get to the next one.
While you're moving the microphone to the next questioner, I wanted to make a comment that it reminded me of. Nobody's brought this up yet, but obviously, we are probably not going to go from chemical rockets and solar ion to interstellar propulsion with no intermediate steps. So one of the things that we look at when we're talking about what makes a good or a bad technology investment is some of these are very clearly enabling at earlier stages of much more aggressive outer planet missions, and given the choice of two technologies to invest in, one of which will, not do anything interesting until you're ready to go to Proxima Centauri, and one of which might get you to Jupiter in a year, in 5 or 10 years from now, the second one's probably a more interesting place to put your technology bet. And so there's a lot of implications for things that go way beyond interstellar in some subset of these propulsion technologies, and that's part of what makes them interesting.
When Breakthrough Starshot was announced in 2016, the point design that was presented was a phased array laser beamer, 10 kilometers in diameter, 70 gigawatts, pushing a 1 meter, 1 gram sail to 20% light speed over about a lunar orbit distance. And Kevin Parkin today presented, sort of an updated point design. The numbers have changed a little bit, but that's still the point design. The panel seems very receptive to exploring other concepts, other approaches, and that's good. But if that is still the point design that's there today, what are you losing sleep over? And particularly people that are directly advising the project, maybe Professor Atwater or anyone else on the panel, what should we be worrying about? What could be the potential showstopper? And maybe that is a way to better organize the research that needs to be done.
Well, let's see. Kevin can chime in as well here, but a very interesting feature of Kevin's model is that it is not only a technical model, it's a techno-economic model. And one of the reasons that we're hovering around this point design, give and take an order of magnitude and various independent parameters, has to do with cost. If we can identify inexpensive or more efficient propulsion technologies that look viable, I think that would be very interesting. But I think that's one of the reasons that is happening. What are the things that we lose sleep over? I guess everybody has a different one, but for me, it's really validating that we have the ability to create some passively stable beam sail riding combinations. The sail is going to be going so fast at the end of its impulse that there's no opportunity for feedback and control. So we really have to have, and I would like to have, not just one concept that we think works, but multiple concepts that we're pretty sure might work. So I think if we can come up with, 2 or 3, 4 good ideas, then I'd be a lot more confident. And I think we're getting there. We've made significant progress in the conceptually. We need to just show that a few of these things actually work.
So just to answer your question briefly, I mean, one of the things I've started working on was particle bombardment, as you know, as you're researching, and also you, I guess. But I'm also interested in the segmented lens array concept, which is a space-based architecture that Jeff Landis came up with. Is Jeff here still? I actually favor that method, the space-based beaming approach. I understand why Starshot's gone to a ground-based beaming approach, because obviously we want to achieve the mission sooner. But I think that in the long term, a space-based beaming approach is much better. And this, of course, is essentially what people like Gerald and Neil were thinking about when they were thinking about the L5 colony, and having solar collectors, and you could power beam energy to satellites and to the Earth, to the national grid. And so I think that's the future
Also, it
direction.
overcomes the atmospheric correction problem.
Yeah, well, yeah, I think actually we've sort of understood that quite well at the moment, and Kevin can say more about that. But what I wanted to say is, what keeps me up at night, I think, is actually going back to Avi's original question about detecting other life, other signatures in the universe. If we can send something that's a gram in size, at 20% the speed of light to the stars, probably in the future, if we carry on scaling that technology up, we can do even better. Maybe we can go faster, maybe we can go smaller, whatever. Maybe we can send bigger things. But it begs the question that, well, somebody could do the same to us. And so, one of the ways to start to address, for example, the Fermi paradox is, well, can we detect all these little micrometeorites which come through and hit the ISS? Or are any of them actually tiny little Star-Wisp probes sent from another civilization? And so that's the sort of things that keeps me up at night. And actually, I find it exciting, but anyway.
I'd actually like to chime in on that one. So the things that actually worry me the most are not technical. They're economic and sort of sociological. I think no matter how you slice this, it's a long-term effort that's going to cost a lot of money, right? It's a huge investment over long term, and I think those are always difficult things to pull off. It took us, a decade to go to the moon, and you could argue that was largely because we had this perceived, at least, existential threat, right? And I don't know. Yeah, I think that's the part that worries me, is what's going to keep us motivated, keep us kind of organized, and keep us pushing forward.
I'll just chime in too. I think the unknown in interstellar space, obviously satellites are built very robust now, but when we first started launching, we had a lot of anomalies and failures because we didn't have a really good understanding of the space environment. So even though we know, or we have a good idea of what's out in interstellar space, I still think that environment's not well characterized.
I want to chime in, but after Kevin.
I just wanted to respond to the point designs. Point designs are just a starting point to perfect the model and to look at its outputs relative to earlier models. But we're getting to the point now where we can start to question the original assumptions, look at what happens when we vary them, and look at design trade-offs and generate requirements. So there has been a lot of looking at point designs, and now we're able to what they call explore the trade space for this. And there are many things that keep me up at night for Starshot. I don't know. Sorry?
Would you articulate one of them? It would be helpful for the community to know what problems we should be focused on.
Well, so actually I should say Starshot is driven by retiring all of the technical risks. We have a prioritized list of risks, and our job is to retire those risks. One of the risks that keeps us awake is phasing the elements of the beam director. So it's being able to form a coherent beam at the thing that you're pointing at. One of the other ones that I worry about, and I think is perhaps going to turn out to be the hardest thing, is to use the sailcraft as an optical element. So no matter which way you use it, you have to control a wavefront over an area or over a diameter of maybe 5 meters to a 30th of a wavelength in one way or another. And I think that's going to end up being very hard. But you have to prioritize which risks you can retire first. So I think we're starting with the things that we can do now, and that's the important thing.
So I have a day job that involves power beaming. I would really like to buy these megawatts of laser power at a cent a watt. I priced it 2 weeks ago at $166 a watt. And that was in 10 megawatt quantity. So I was already getting the volume discount from the leading provider of fiber lasers. So I appreciate fully that the argument that there's a Moore's law-like power curve for lasers, and lasers are getting cheaper. They have been getting cheaper. They will be continuing to get cheaper. But one of the challenges that I face switching hats and thinking about my Tau Zero hat is that's true for a lot of technologies. So you have to be careful not to be comparing. If you're picking a technology path of goodness, you have to be careful not to comparing technology A as I think it will be in 40 years to technology B as it was last Tuesday. Technology B may also be on its own technological improvement curve, and you have to be sure that you're comparing an apple to an orange, or at least from the same decade. So there's an enormous, as you know very well, there's an enormous number of really exciting beam power applications. Long before you get to gigawatts, at mere megawatts, there's a lot of really cool stuff that we could be doing. But the challenge with beam power is if you want to get good range, you got to go to optical frequencies. That makes the dollar per watt of the beam get expensive. If you want to go to cheaper beams, you got to go to lower frequencies. That makes the range shorter or the aperture get really big, and that's got its own challenges. So we're really on the threshold of a lot of cool stuff on beam power, but I worry a little bit that we're letting our vision for how much better we think it will be in the future. I think the community may not be appreciating that that is our vision for where it's going to be in the future and not necessarily the present of where it is today.
To respond to that also, I completely agree. But maybe a useful sort of shift of reference frame is from Moore's law to what economists or business school people would call a progress curve. And that's a cost per unit functional element versus the volume of elements that are produced. And almost all technologies and almost all industries, integrated circuits, lasers, hard drives, all kind of electronics technologies have cost volume curves that have an 80%. When you double the output, the cost drops by 20%. Almost all of them are the same. So we should be looking for the technologies that are going to expand and have widely expanding markets for something else other than Starshot, or where Starshot can account for those order of magnitude increases in the volume of the technologies. Because the progress is actually the cumulative hard, engineering progress that's made by engineers staying up, nights and weekends, solving problems as the market expands. Yeah.
So we're getting kind of close to closing remarks time here, and there's one thing I would actually like to bring up. So this is a long-term effort, and we've been talking about a lot of technical things, but I'd also like to raise the point that many of us won't be around if and when this thing eventually happens, right? It's going to take a while. So we need to also sustain interest in these problems and kind of get the next generation interested in it. Not that that's necessarily a problem, but Elena, as someone who worked on these things for your master's degree, what do you think about sort of student engagement in these issues and getting young people involved?
Well, of course, with students, you get many chances to catch the attention of everyone when you start talking about interstellar travel and those topics. But it can be very hard to find a way to get into the community and to start actually working on these topics, because there's really few people in the world connected with each other on this topic. And maybe if you do some study on more, let's say, practical stuff, it's gonna be much easier to find, let's say, some space to practice. I was really lucky to get the chance and to go at the CUNY City Tech to do my master thesis study. And actually, I got involved also with Kelvin in the Initiative for Interstellar Studies, and last year we organized a conference in New York again. So I feel really lucky to be part of this. And I know there's many people, many young students that would really like to be in the same position to share their ideas on this topic, but it seems like it's a really closed environment at the moment.
So what can we do to fix that?
I mean, one example for students how they got much engaged was, for example, with CubeSat. CubeSat opened much more opportunities for universities to have small projects where everyone could actually practice and grow up in these studies. And I guess, okay, you cannot plan an interstellar mission for a small university project, but at least some kind of studies could be associated to these also. That's what I would say.
right.
I also mention real quick that we've had a couple of students in the lab, and they were paid for by the Space Studies Institute. So they have an exotic propulsion program, and you can make small donations, and then they can support students that come work with us. So that's another way to go. Space Studies Institute.
Just to say, I think actually the problem slightly solves itself, because Arthur C. Clarke said that the purpose of astronomy is the perpetual astonishment of humankind. Right? So as long as there are stars in the sky and we can see them, I think even if you have ebbs and flows of human progress and people start to look up the stars and they wonder, hopefully at some point you get technology going again no matter what happens, and you eventually get out there. Just to leave you on a sobering thought, I'm an advocate for interstellar flight, but actually intergalactic flight is a very different problem altogether, because the galaxy is 100,000 light years across. Now for those who've read Isaac Asimov's Foundation series, they would be aware of psychohistory. Psychohistory, of course, doesn't really work because you require a vast number of particles if you base it on statistical mechanics. And human beings, as Asimov said himself, are much more complicated than individual particles. So in terms of human beings actually getting to other galaxies, unless you're going to go relativistic and then you've got the time dilation factor, it's so far away. With all the propulsion systems we're talking about at the moment, from Orion-type systems to fusion to laser beamers, you're talking about tens or hundreds of light years at best. To actually go much further than that, to the edge of the galaxy, which is 100,000 light years across and beyond, it's a much more difficult problem. And it's exciting, but it's also sobering, I think.
So there'll still be something for the next generation to do.
I don't think we doubt that.
Is it working? Yeah,
there you go.
Sorry, just to follow up on that, I would take a lesson from astrobiology, because I was at NASA Ames 20 years ago, and I've been in New Zealand for 20 years, and what I see is an absolute explosion, and you saw some of that excitement the other day. How about if physics opens up and starts really supporting students, because so much of what's happening in our progress in astrobiology has come from an absolute, the students are so excited, but we've created, you don't just wait for that to happen passively. The professionals need to get seriously involved with mentoring, tutoring, CubeSat missions, whatever. I know you're not going to send these students into interstellar space, but we have had the most incredible renaissance, which will lead some of the big questions that you guys are creating this machinery for us to do. So I do hope that physics opens up, and particularly for people of non-traditional backgrounds.
Great, thanks. And with that, oh, sorry, is there? Okay. We are out of time, so thank you to our panel, and thanks to everyone.
Thanks, guys.